Assalamualaikum. In this presentation, we will divide into one of the most powerful and versatile tools in modern analytical chemistry, high-performance liquid chromatography, or simplified HPLC. HPLC has become a cornerstone in various fields, from pharmaceuticals and food safety to environmental science and biotechnology. Whether it's ensuring the purity of a new drug, detecting contaminants in water, or analyzing complex mixture, HPLC has revolutionized how we approach chemical analysis. Over the next 10 minutes, we will guide you through the fundamentals of HPLC. High-performance liquid chromatography (HPLC) is a technique that uses a liquid mobile phase to separate components in a mixture. The analytes are dissolved in a solvent and pushed through a column under high pressure. HPLC is highly versatile, capable of separating a wide range of chemical mixture, including non-volatile and thermally unstable compounds such as organic and inorganic substances, biological samples, synthetic and natural polymers, and thermally labeled compounds. The advantage of HPLC include high sensitivity due to various detectors, reusable columns that allow for multiple analysis, suitability for ionic species and large molecules, and the ability to recover sample using fraction collectors. The principle of HPLC involves injecting the analytes onto the top of the column, where separation occurs as the analyte moves with the mobile phase through the column. Each component exits the column as a peak on the recorder, and the detectors respond to these components is displayed as a chromatogram. The objective is to determine the retention time of a standard solution, caffeine, to identify the caffeine peak in a soft drink sample, and to determine the amount of caffeine in a soft drink sample using a response factor method.
Now we move on to the next part, which is the methodology. In this part, I will introduce the instrument we use in high performance liquid chromatography (HPLC), and I will explain the function of its main components. To start with, we have the mobile phase reservoir and filtering. The mobile phase reservoir serves to hold the solvent, and the filtering system protects the column by preventing clogging, which could reduce separation efficiency and require more frequent column replacements. Additionally, it prevents the contamination of the sample, which could interfere with the analysis. Other than that, we have pump. The pump is essential in HPLC as it ensures a steady pulsation-free flow of the mobile phase through the system. This stable flow is critical for maintaining the consistency and accuracy of the analysis. Next is the injectors. Injectors play a crucial role in introducing the samples into the mobile phase. They work alongside with several components, which is the shrink injection. This is the simplest method for introducing samples. Also, we have sampling loops where it holds the sample temporarily before it is injected into the system. And lastly, autosampler, where they automatically inject large number of samples, streamlining the process and minimizing the needs for manual inputs. Moreover, we have the column. The column is the heart of the HPLC system, where the separation analytes occurs. In HPLC, the analytical column is the main component where the separation of analytes occurs based on their interaction with the stationary phase. The guard column that placed before the analytical column helps to trap the impurities and particulate matter to protect the analytical column from clogging while extending its lifetime. The guard column also minimizes band broadening and prevents the deactivation caused by the absorption. Finally is the detectors. Detectors identify the analytes as they exit the column. There are two basic types of detectors, which is the bulk detectors. This responds to a mobile phase bulk property such as refractive index. Second is the solid property detectors. This responds to some property of solid such as UV absorbance. Now that concludes my section on the methodology. Thank you for listening. I will now hand over the presentation to IZZAH.
So this is the results. Based on the results, we have three compounds, which are standard caffeine, coke, and Levita. First and foremost, the retention time of the compounds were determined based on the chromatogram. The retention time of standard caffeine was based on the highest peak in the chromatogram of the compound. Standard caffeine compound was used as a reference. The retention time of Coke and Levita was determined based on which peak is the closest with the standard caffeine peak's value. From that, we got our retention time value for each compounds, which are standard caffeine is 2.482, Coke is 2.481, and Levita is 2.479. Furthermore, we identified the peak area of caffeine in each compounds. The peak area was automatically identified after we have determined the retention time of each compounds. The peak area of standard caffeine was 6249.48779, Coke was 7001.12305, and lastly Levita was 11154.10. So now I will be talking about the discussion. The analysis of chromatograms in HPLC depends on two key factors, which is retention time and peak areas. Retention time, which is the duration of compartments in the column before detection, is distinctive for each compound under stable chromatographic conditions and serves to identify analytes. In this examination, the retention times for standard caffeine is 2.482 minutes, Coke is 2.481 minutes, and Levita is 2.479 minutes, are almost the same, indicating that the peaks in the samples relate to caffeine. Retention time is selected for comparison as it indicates the compound's interaction with the stationary phase and its solubility in the mobile phase, providing specificity in identification. Minor variations in retention time, like those noted here, can arise from experimental factors such as column degradation, temperature changes, or sample handling. Yet the strong correlation confirms the alignment. The peak area measures the caffeine concentration using the standard caffeine area, which is 6249.49 as a reference point. The greater peak values for Coke is 701.12 and Levita is 11154.10, suggest elevated caffeine levels in the samples. The analysis of retention times and peak areas underscores the efficiency of HPLC in isolating and measuring caffeine functioning by leveraging variations in compound purity and their interactions with the stationary and mobile phases, thus guaranteeing precise identification and measurement.
Coke and Levita using the peak area from the chromatogram. Let's go through the first step. First, we need to calculate the response factor or RF using the caffeine standard solution. We know that the concentration of the standard solution is 0.1 mg per milliliter and its peak area from the chromatogram is 6,249.48739. To find the RF, we divide the peak area of the standard by the concentration of the standard, and the result is 62,494.8739. This RF will be used to determine the caffeine concentration in the ALYA sample. Next, we calculate the caffeine concentration in both Coke and Levita using the formula caffeine concentration equal to peak area of the sample divided RF. So for Coke, the peak area of caffeine in Coke is 7,001.12305. Then we divide by the RF, and then we get the result is 0.112 mg per milliliter. To convert this per million ppm, we multiply by 1000, so the result is 112 ppm. This is the concentration of caffeine in Coke. Similarly, the peak area of caffeine in Levita is 11,154.10000. Dividing by the RF, we get the 0.178 mg per milliliter. We convert it to ppm, then get the concentration of caffeine in Levita is 178 ppm. To summarize, we calculate the caffeine concentration by determining the response factor from the standard solution and apply it to the peak area of the ALYA sample. This method shows us how to quantify the caffeine content in different beverages accurately using chromatographic data. In this experiment, the goals were successfully met. The retention time of the standard caffeine solution was established, the caffeine peak in the beverage sample was recognized, and the caffeine quantity in the beverage sample was computed using the response factor approach. The HPLC system turned out to be a dependable and accurate instrument for this evaluation, showcasing its effectiveness in both quantitative and qualitative analysis. In addition to caffeine analysis, HPLC is extensively employed in numerous applications such as the separation and examination of pharmaceutical substances, food additiveness, environmental pollutant, and biological specimen. The findings from this experiment offer important information regarding the caffeine level in soft drink and further illustrate the adaptability of HPLC as an essential tool in analytical chemistry.